Good morning. Today I will present our work, which is a comparison study of co-simulation frameworks for multi-energy systems. In particular, we are going to focus on the scalability problem. I am Pietro Rando and I am a PhD student at the Politecnico di Torino. Starting with a bit of context, nowadays our energetic infrastructures, no matter what typology we are taking into consideration, are gaining in complexity. New concepts and new actors are taking place, and a case in point of this phenomenon is the multi-energy system. Multi-energy systems combine different energy vectors and are composed by a large number of components, such as the energy networks themselves, the consumer that can become prosumers, the distributed energy resources, storage systems, communication networks, and so on. Due to the high number of components interacting within each other in this kind of system, multi-energy systems can be acknowledged as complex systems. They can be addressed from several different perspectives. Thus, the study of this system will need different expertises from different fields. Then, in order to properly assess them, there is the huge need of a tool capable of capturing their multifaceted nature. Co-simulation comes into play and answers for this need. Co-simulation allows to simulate and integrate different domain simulators in the same co-simulation environment. In literature, several different solutions and frameworks are present that address this topic, in particular for what concerns smart grid. Here we present some examples of this, especially focusing on the multi-energy applications. Our objective is to perform a framework comparison in order to better understand them and to help in choosing the right tool for the right application. In particular, we will focus on the scalability. Scalability is the ability of the co-simulation framework to increase the amount of heterogeneous simulator and model instances both vertically in the same node and horizontally on different nodes, distributing the problem. The chosen framework for the comparison are especially Mosaik and HELICS, which among the multitude of co-simulation frameworks for smart grids are the more generalizable and more prone for the multi-energy system extension. In addition to this, we have chosen them because our work is based on the baseline of Steinbrück et al. 2017, which compared high-level architecture standards such as HELICS with Mosaics, without taking into consideration the scalability perspective. Finally, we also included the AIOMAS library, which is a Python library used to build multi-agent systems, and later on we will explain our parallelism between the co-simulation frameworks and the multi-agent system. Co-simulation frameworks have a common architecture that can be generalized by analyzing its components. Every co-simulation framework must have a scenario, which is the representation of the case study and allows to instantiate simulators and explicitly implement the relationships among them. Then we have the orchestrator, which is the core of the co-simulation because it manages time regulation, synchronization, and data exchange among all the entities involved in the framework. Then there are the simulator, which instantiate the model, creating the model instances. They act as interfaces for the model instances to communicate. Then there are the model instances, which are the actual representation of the physical components, and they actually simulate the behavior of the physical components in the real world. Before starting with the experimental section, we have designed some benchmark configurations. The first one is the classic simulation. When, for example, we are using Mosaik or HELICS, we face with this kind of configuration. It consists in a configuration for which each single node can manage only a single process. Each process is a simulator process that can manage more than one model instance. Then there is an extension to the previous one, which is the multi-process co-simulation. In this case, it simply enables the nodes to manage more than one process. In this case, we can associate more than one simulator with the related model instances to a single computational node. Then we have the multi-agent as a co-simulation configuration, which is why we have introduced AIOMAS. In this case, we have used the multi-agent system library to build up a custom co-simulation framework. It is distributed and multi-process thanks to the deployment of containers. Synchronization, data exchange, and time regulation are done through the clock and the remote procedure calls, which are embedded functionalities in the AIOMAS containers. Actually, what we are doing here is to collapse the concept of simulators and model instance in a single entity, which will be the agent. At this point, the agent will be able to represent the physical component, simulate its behavior, and also take the responsibility for the communication itself with other entities. Finally, the classic simulation with encapsulated multi-agent system is when we want to integrate a fully functional multi-agent system environment into a co-simulation one. In this case, the simulator will act as an interface between the whole co-simulation infrastructure and the whole multi-agent system environment that will simulate autonomously. Here we present our case study. We choose a multi-model energy scenario, rather simple in order to avoid that complex dynamics affect the timing performances of the simulations. It mainly consists of 4 actors. The first one is the meteo simulator, which is a stateless simulator in charge of communicating weather-like information to the others. Then there's the photovoltaic simulators, which simulates the behavior and estimate the power production of the photovoltaic unit. And finally, we have the building simulator, which simulates the thermal behavior of the building, estimating the load demand and translating it into a power electrical load demand thanks to the embedded heat pump model. Finally, the last one is the power grid simulator, which once has acknowledged all the data for production and demand from the other simulator, will simulate the physical behavior of the power network. This table summarizes all the configuration that we have tested in our work. Starting from the top, we have 2 classic co-simulation configurations, one for Mosaik and one for HELICS. Then at the third place, we have the multi-agent system as a co-simulation configuration. Then we have 2 configurations for the multi-process co-simulation, one for Mosaik and one for HELICS. And finally, 2 configurations for the multi-agent system embedded into co-simulation, one for Mosaik and one for HELICS, taking into consideration that for both the cases, the multi-agent system environment has been implemented exploiting AIOMAS. For all of this configuration, we have tested them ranging from 1 model instance up to 1 million. In order to evaluate the scaling performance, we designed 3 temporal key performance indicators. The first one is the setup execution time. It takes into account all the initialization phase before the actual start of the simulation. Then we have the average time step duration, which is actually taken during the simulation, and it represents the average time need to perform a single simulative step. Then we have the final one, which is the total execution time, that it speaks by itself, but it actually is the time needed to each configuration to conclude a whole simulation cycle that in our case is of 48 hours with 1 hour time resolution. Here we have the first results, the setup time duration. And as a first consideration, we can say, and this will hold for all the next results, that we can see that all configurations involving Mosaik, due to an intrinsic limitation of Mosaik itself, cannot scale up above the 10,000 instances. For the setup time execution, we can also see that the best performing solution are the one with HELICS, and in particular we can see that before the 10,000 instances, the setup time does not benefit in the multiprocess configuration of the multiprocess itself. It only starts to take advantage of the multiprocess configuration from above the 10,000 model instances. Then we can see the different behavior of Mosaik multiprocess and Mosaik AIOMAS. For Mosaik multiprocess, we can see a huge rise in the setup time duration from 1 model instance to 100 model instances, and this is due to the fact that we are starting the multiprocessing, and that requires a bit of overhead in the setup. This holds also for Mosaik AIOMAS, but having developed the Mosaik AIOMAS configuration with a threshold on which to start the multiprocess, which is 100 model instances, we can see that the rise is just above the 100 model instances. Then we have the average time step duration. This actually can give us the idea of the actual simulative performances for each one of these configuration. And also in this case, we can see that for the really largest scale, HELICS multiprocesses outperforms the others. But then, focusing on the smaller and medium scale scenarios, we can see that up to 10,000 model instances, the difference are really small. And thus, all of these configurations are suitable for small to medium scenario. Finally, we have the total execution time. This is a composition of both setup time and average time step duration, and it behaves very similarly to the second one because it's the more influencing factor, especially in a simulation of 48 hours. Also from this graph, we can see the outstanding performances of multi-process HELICS. Finally, to draw some conclusion, we can see, of course, that the best performing tool in terms of scaling up is HELICS with multiprocess configuration. We can also say that multiprocess configuration increased the scalability performances, especially from 10,000 model instances and on. Then we can say that Mosaik is more suitable for medium to small scenarios and is also the most intuitive tools to be used among the one tested. And finally, two considerations on the multi-agent system. The first one is that using it as a simulation does not improve in terms of scalability performance, but is suitable in case we wanted to assess highly customized scenarios because all the implementation is up to the researcher. Finally, integrating multi-agent system in co-simulation framework also does not improve scalability, but can offer some opportunities. For example, if we need to test a really populated and complex system with highly interacting agents and we want it to simulate separately from the simulation framework, we can use strategies like this one. In conclusion, we can say that we have highlighted some future works that we are willing to do. The first one is the standardization of the benchmarking, taking into account the fact that different simulator typologies will have different effects on the performances. Then we wanted also to test how different workflow and data exchange interaction can affect the scalability performances. And finally, we wanted to design some ad hoc key performance indicators that are able to take into account the above-mentioned features. So thanks a lot for your attention. I'm Pietro and if you have any questions, I'm here.